እንደምን አላችሁ የሳፔሪ አካዳሚ ተከታታዮች። በዛሬው ሁለተኛው ተከታታይ ቪዲዮአችን ስለ ቴርሞዳይናሚክስ ያሉት ጥያቄዎች የምንጀምረው በዛሬው ከኩዌስችን ነምበር 24 እስከ 21 ያሉትን ከቨር እናደርጋለን። ጥያቄዎቹን እዛ ላይ በሳፔሪ አካዳሚ ቴሌግራማችን @ሳፔሬ አካዳሚ ላይ ጥያቄዎች አሉ። እነሱን እያያችሁ ከዚህ መልሶቹ ጋር መሄድ ትችላላችሁ ማለት ነው። 24 እንጀምር። About 24 it says that we have a heat engine. We have a heat engine አለን. A heat engine which is operating between ሁለት temperature reservoir መካከል. We have a very high temperature reservoir of 200 degrees Celsius which is ወደ ኬልቪን ሲቀየር is equal to 473 ኬልቪን እና at a colder reservoir 80 degrees Celsius ላይ የሚሰራ በኬልቪን ሲቀየር 353 ኬልቪን ላይ የሚሰራ ሁለት ቴምፕሬቸር ስኬሎች አሉ። Now it also says that this machine achieves 20% of the maximum possible efficiency ነው የሚለው። Now when we talk about efficiency ያለፈው we have seen two kinds of efficiencies and these are simply normal efficiency እና the most maximum theoretical ወይም ደግሞ Carnot efficiency ብሎን አይተናል። Carnot efficiency. Now always Carnot efficiency is greater than the normal efficiency of any machine. Now እዚህ ጋር ምንድነው የሚለው the efficiency of the system is 20% of the theoretical or Carnot efficiency ነው የሚለው. That is E is 0.2 times Carnot efficiency ያለን ነው. So this is and በኢኩዌሽኑ መሰረት እናውቀው. And also says that if what will enable the engine to perform that work done of the engine of 10 kilojoules of work ለመስራት what will enable the machine now heat engines work by taking in some heat QH, expelling some work and then also expelling some value QC ወደ ውጪ ነው. And thus the amount of energy that will enable the machine to do a work must equal to QH. So that's that question ምንድነው is what would be the value of QH. Now to solve this question we can use the equation, that is the equation led by the Carnot maximum efficiency which is a 1 minus of TC over TH. Now from this equation we can easily see that 1 minus EC is TC over TH, implying that from this amount of equation by Z I can find TH, I can find TC, but since these two are given, EC ቀጥታ ማግኘት እችላለሁ. So my value of EC, that's the Carnot efficiency, is 1 minus TC, 353 Kelvin over 473 Kelvin. Kelvin ይጣፋል. This it becomes a 1 minus of some value, which is equal to 0.253. So this is my Carnot's efficiency. But I have seen that the efficiency E is working at 20% of the Carnot's efficiency. That E is 0.2 times the Carnot's efficiency. That's 0.2 multiplied by the Carnot's efficiency of 0.253 is going to yield a value of 0.0506. So this is the efficiency of the system. Now if the efficiency of the heat engine is found to be 0.0506. Now normally efficiency of the heat engine is given by what we get, that is the amount of heat by the engine over what we put in, that's the amount of QH. So that's my value of QH equals to work done of the engine divided for the efficiency. Work done by the engine is 10 kilojoules over an efficiency of 0.0506 is going to yield 197.6 kilojoules. So my value of QH is 197.6 kilojoules ማለት ነው. For the question number 23 ስናልፍ we have a refrigerator which has a cope. Now cope እዚህ ጋር cooling mode ነው የምናየው refrigerator ስለሆነ which equals to 5. Now the refrigerator takes in 120 joules of energy from a cold reservoir. በዛ ማለት my value of QC የሚወስደው is 120 joules each side. So A, what is the work done? The work done on the engine ነው እዚህ ጋር የምናየው remember. And B, the amount of heat that it expels ወይም QH no. Now cope for heating mode for cooling mode እዚህ ጋር is equal to QC divided for the amount of work done by the engine አይደለ? So that's the work by the engine equal to QC over cope ነው የመጣው which is 120 joules over 5, which is 24 joules. The next is what is QH. Now in a kind of refrigerator ወይም ደግሞ እዚህ ጋር heat pump የሚባሉት እንሰራቸው እዚህ ጋር work አለ አይደለ? So they take in ከዚህ ወደ ላይ they take in a value of QC and they expel a value of QH while work is simply being performed. ስለዚህ እዚህ ውስጥ ያለ ምንድነው? we're going to have some QC plus some work አለን. So እዚህ ጋር QC plus some work ከተሰራ በኋላ is going to be expelled to the value of QH. And thus my value of QH, which is going to be expelled, is QC plus of work of the engine. So QC is given as 120 joules plus work done by the engine is 24 joules. So this is 144 joules. So 144 joules of heat must be removed by the refrigerator so that it can make so that it would work at an efficiency of 5. ወደ ጥያቄ ስናልፍ የሚቀጥለው ጥያቄ number 22. A particular heat engine has a power output. So the power output of the engine is 5 kilowatts or simply 5000 watts. ከፈለግን ይሄ ለዩኒታችን that's about 5000 joules per second ማለት ነው. And an efficiency, it has an efficiency E of 25%, which is 0.25. Now the engine expels 8000 joules of exhaust energy in each cycle. So expel የሚያደርገው that's my value of QC is equal to 8000 joules or 8 kilojoules in each cycle. So A, what is the amount of heat it taken? And B, what is the time that it takes for it to finish one cycle? Now for any kind of heat engine, the amount of E, that is my efficiency, can be given as what we gain. That's the work done by the engine over what we give, which is QH. But we know that the amount of our value of QH is going to be equal to engine now. So this equation is going to equal because we know that the work done by the engine is QH sickness QC over QH, right? Which is going to simplify to 1 minus QC over QH simplify. So our efficiency E is 1 minus QC over QH. Now from here we can observe that 1 minus E is equal to QC over QH, and thus QH is equal to QC divided 4 to QC divided 4 1 minus E. And so QH is what's my value of QC. I have been given Ziga. My QC is 8000 joules. Sikafel for 1 minus 0.25. That is 8000 joules over 0.75, which simply gives me 10.67 kilojoules. So 10.67 kilojoules of heat must be absorbed by system. And now the next question is what's the time? Now power is given as work over T. In this case, work action is going to equal to the work done by the engine. So from this equation, time is going to equal to the work done by the engine divided for the power. Now from this equation, work done by the engine can be given as the value of QH minus QC. So time is going to equal to QH minus QC over T. What is QH? That's a 10.67 kilojoules sickness 8 kilojoules over this is power over power action demo 5 kilojoule watt የሆነውን joule per second አርግተናል አይደለ ወይም kilojoule እዚህ so 5 kilojoules per second. So this is equal to 2.67 kilojoules over 5 kilojoules per second. So by dimensional analysis, kilojoule by kilojoule ይጣፋል, and then I'm left with 0.534, approximately 0.5 second ነው የሚወስድበት ማለት ነው። So this is the answer for question number 22. Now question number 21 ትንሽ ጊዜ ይፈልጋል ይሄ. So እና መጀመሪያ እስካሁን ያየናቸውን የተርሞዳይናሚክ ፕሮሰሶች ማየት ሁለተኛ ላይ ደግሞ እዚህ ጋር የእያንዳንዱን የሞላር ስፔሲፊክ ሂት ካፓሲቲ ማየት አስፈላጊ ነው። So the question says that a diatomic ideal gas, it's diatomic መጀመሪያ, an ideal gas of diatomic ideal gas has an omega of that a gamma of 1.4. Now this is the same as to 7/5 መጀመሪያ. It is confined to a cylinder and is put through a closed cycle. ስለዛ closed cycle ውስጥ እንዲያልፍ ነው የሚደረገው. That closed cycle ውስጥ የሚያልፍ means it's cyclic, implies the change in internal energy is 0. So this means ይሄን equation እዚህ ጋር ያዙት. This means that the amount of work is negative of heat. Now ይሄ እዚህ ጋር በኋላ ይጠቅመናል. The amount of heat. Now initially ነው የሚለው. Initially, that's initial values ልበላቸው. Initially the gas is found at P1, at V1, and at some temperature, T1. Now, first, the gas's pressure is tripled under constant volume. Now, under constant volume means isochorically, so isochorically, the gas's pressure, P1, triple ያደርጋል ማለት ወደ 3P1 የሚወሰደው ማለት ነው, right? Or ከፈለግን P2 is going to equal to 3P1. This is our first step. And then it expands adiabatically. So at the second one, adiabatically expand ያደርጋል. So V1 ወደ V2 ይሄዳል. Expands adiabatically to its original pressure And then P2 ወደ P1 ይመለሳል. Original pressure. And finally መጨረሻ ላይ ደግሞ it is compressed isobarically. So isobarically it is compressed. ስለዛ to return ከV2 ወደ V1 ይመለሳል. So this is our given data. So our given data is the gas, this pressure increases isochorically from P1 ወደ 3 triple. We also see adiabatically ደግሞ the volume increases while the pressure is returned to its original position. Isobarically ደግሞ it goes from some V2 ወደ V1 ይሄዳል. So አሁን ይሄን በስነ ስርዓት ያሉት. ስለዛ let me try to draw our graph እዚህ ጋር PV ግራፋችንን ለመሳል. So this is my volume and this is my pressure. So initially እዚህ ጋር ይገኛል ልበል. This is initially. So initially I have a volume of V1 and the pressure of P1. So at at original process line, isochorically pressure triple ያደርጋል. So isochorically ከሄደ በአንድ V ላይ ከዚህ ቮልዩሙ ሳይቀየር ማለት ነው ወደ 3P1 ይነሳል. So isochorically ወደዚህ ይሄዳል. This is my isochoric process. In the second process, adiabatically it expands. ከV1 ወደ የሆነ V2 ነው የሚሄደው. በምን adiabatically. So የadiabatic ፕሮሰሶች ግራፍ ደግሞ it's a curve ወደ ታች. ይሄ አይሶተርም ነው የሚባለው. So ወደዚህ ይሄዳል. እዚህ ጋር ደግሞ የሆነ ቮልዩም V2 ይመለሳል. ፕሬሸሩ is the same. And at last ደግሞ isobarically at constant pressure ማለት ነው. So isobarically at constant pressure ከV2 ወደ V1 ይመለሳል. So this is going to be my graph ማለት ነው. Now እነዚህን ልሰይማችሁ for easy እንዲሆኑልን. I'm going to call this position A, I'm going to call this position B, and I'm going to call this position C ልበለው. So my system goes from A to B and then from B to C, ከዛ from C ደግሞ to A ይመለሳል. Now ይሄን በስነ ስርዓቱ ያዙት. This position ግራፉን. This is what A is going to look like. Now at question የሚቀጥለው question ላይ ስናልፍ B, what is the V final at the end of the adiabatic expansion? V final at end of an adiabatic expansion. Now ወደ ኋላ ተመልሰን ስናይ so the final volume at the end of the adiabatic expansion የሚለው. So the end of the adiabatic expansion ማለት is this one. At C is the end of the adiabatic expansion. ስለዛ እዚህ ጋር ያለው ቮሊዩም ምንድነው? Now B ላይ ያሉት let us call them PB ልበለው. እዚህ ጋር ያለውን pressure VB TB ልበለው. እዚህ ጋር ያለውን PA VA TA ልበለው. at C ላይ ደግሞ ያለኝን PC VC TC ልበለው። So the question is, what is VC ነው የሚለው። Now VC ለማግኘት remember that this is an adiabatic process. ስለዛ for adiabatic expansion of gases we have seen under relation assume that is P multiplied by PV to gamma is a constant የሚል and relation አይተን ነበር. So this could be expanded to P1 V1 gamma equals to P2 V2 gamma expand ሊያደርግ ይቻላል. Now P1 V1 የሚባለው it's at the start of the adiabatic process ላይ ያለው ይሄ ደግሞ at the end of the adiabatic process ላይ ያለው ነው. Now the start of the adiabatic process ማለት እዚህ ጋር while the end of the adiabatic process ማለት እዚህ ጋር. Now እዚህ ጋር ከእንደገና አንዴ ግራፉን አሳጠሪው እዚህ ጋር ብስለው so እዚች ጋር ማለት ነው. Now we know that this እዚህ ጋር ያገኘሁት equation P1 V1 ምናምን በC እና በA በተካው this is A, this is B, this is C ብለናል. I get PV VB gamma equals to PC VC gamma. But I know that PB እዚህ ጋር ያለው pressure is triple that of A አይደለ? That is PB 3 times PA ነው. triple አደረገ ስለሚል that's 3 times PA multiplied. VB is also the same as to VA because this process is isochoric. The volume doesn't change. Underline the line is the same. So VB is the same as to VA equals to PC. This is my pressure at C. Ziga is also the same as PA አይደለ? Because they're simply found on the same line because you're the Z line. So this is also the same as to PA times VC to gamma Z gamma አለኝ. So PA and PA remove ባረግ I have 3 VA to the gamma equals to VC gamma. So from this equation ሁለቱንም side by 1 over gamma ባባዛቸው 3 times 1 over gamma multiplied by VA equals to VC ያገኛለሁ. So my volume at the end of the expansion VC is VA multiplied by 3 of 1 over gamma. But I have seen that gamma is equal to 5 over 7. Is equal to 7 over 5 አይደለ? This is what gamma is. መጀመሪያ ሲጀምር here gamma is 7 over 5 ብያለሁ. So ይሄን እዚህ ጋር ቀጥታ እዚህ ጋር በከተው gamma is 7 over 5 ከሆነ 1 over gamma 5 over 7 ይመጣል አይደለ? So VC is equal to VA times 3 of 5 over 7 ማለት ነው. While VC ከፈለጋችሁ V2 በሉት. V2 V1 times 3 of 5 over 7. ይሄን ከሰራችሁት 3 to the 5 over 7 is approximately ወደ 2.19 ጋር እኩል ነው. So V2 is 2.19 V1 ማለት ትችላላችሁ ማለት ነው. So this is our answer. Now the second question, the third ላይ ደግሞ the third የሚጠይቀን ምንድነው? Question number 21. Find the temperature of the gas at the start of the adiabatic expansion. At C, የሚጠይቀን what is the temperature of the gas at the start of the adiabatic expansion? At the start, that is T initial temperature at the start of the adiabatic expansion. Now adiabatic expansion የጀመረው ግራፉ ላይ እንደሚታየው የጀመረው እዚህ ጋር ነው. that is TB ማለት ነው በሌላኛው በኩል what is TB ነው የሚጠይቀን. So this is the same as TB is equal to 1. Now ይሄን ለመስራት አንዳንድ ተማሪዎች የሚጠቀሙት ምንድነው? መጀመሪያ የሆነ relation that is T multiplied by V gamma minus 1 is constant ብለው ነው. አሁን ይሄን equation እዚህ ጋር መጠቀም አንችልም because this equation works for adiabatic processes አይደለም? for adiabatic process ነው. እዚህ ጋር at the start of the adiabatic expansion ነው. the process hadn't take place. ፕሮሰሱ ስራ አልጀመረም. ስታርቱ ላይ ነው እዚህ ጋር ሳይጀምር በፊት ላይ ያለው. እዚህ መካከል ላይ ቢሆን ፕሮሰሱ ከተደረገ ቢሆን this equation ይሰራል. እዚህ ጋር ነው ያለው. as a result we cannot use this relationship. ስለዚህ ምን ነው የምንጠቀመው? we use the ideal gas relationship that is at V ከእንደገና ግራፉን እዚህ ጋር ብስለው that's B A እና at C እዚህ ጋር ያለው at P we know that P B V B is nRTB መሆኑን እናውቃለን አይደለ? This is the equation of the ideal gas. But what is PB equal to? We know that PB is triple that of the 3. So that's 3 times PA ነው. This is 3 times PA ይመጣል. We also know that VB is equals to VA ከእንደገና that's VA is nRTB እናገኛለን። Now ይሄን equation ስናይ we arrive at something. እሱ ምንድነው? PAVA ነው የምናገኘው። Now we know that PAVA እንደዛው is nRTA ጋር እኩል ነው አይደለ? እዚህ ጋር ያለውን PA times VA is nRTA እዚህ ጋር ደግሞ PB VB is equal to nRTB ነው። So ይሄን nRTA እዚህ ውስጥ ብከተው 3 times nRTA is equal to nRTB ያገኛለሁ። So nR በnR ባጠፋው TB equals to 3 times TA ያገኛለሁ ማለት ነው። So this is it. So the temperature at the start of the adiabatic expansion is equal is 3 times that of the temperature which is simply found at the start of the isochoric. Now, the start of the adiabatic ማለት በሌላኛው በኩል it is the end of the isochoric ማለት ነው አይደለ? እዚህ ጋር ያለው the start is the end of this isochoric process. So the temperature which is simply found at the start of the adiabatic expansion, which is equal to the temperature at the end of the isochoric expansion, is 3 times the temperature which is simply found at the start of the isochoric expansion ማለት ነው. So this is C. Let us go to D. Now D asks what is the temperature at the end of the cycle. So T final at the end ነው የሚጠይቀው. At the end of the cycle. This one is a relatively easier question. Now at the end, remember that this is a cycle. So this implies that the U initial is the same as the U final, right? So system ስናይ ሳይክሊክ ስለሆነ ከዚሁ ተነስቶ ወደዚህ ሄዶ ወደ ቦታው ነው የሚመለሰው። at the final temperature መጨረሻ ላይ ሲያልቅ is equal to Tm originally ከነበረው ቴምፕሬቸር ጋር ነው ኢኳል የሚሆነው። So Tf at the final temperature is equal to Ta ማለት እችላለሁ ማለት ነው። And now let's go to the pearl of all the equations. Now let us jump to the question of the questions. That is መጨረሻ ላይ ያለው what is the net work done on the gas for this cycle? E work ምንድን ነው የሚሆነው ነው። Now we have seen that this is a cyclic process. So መጀመሪያ ላይ ስንጀምር that is originally ያስቀመጥነው proposition which is that work is equal to negative Q የሚለውን እንጠቀማለን። So here, so work equals to the negative of the heat አይደለ? So what I have to find is the total heat ማለት ነው። Now during my process የሚመስል ግራፊ ውስጥ ከዚህ ወደዚህ I have an isochoric ከዚህ ወደዚህ an adiabatic and ከዚህ ወደዚህ an isobaric process. Now during my isochoric process adiabatic እና my isobaric procesሶች ያሉንን heat መደመር ነው። This is A, this is B, this is C. So the total heat is the heat Q from A to B ሲደመር the heat Q from B to C ሲደመር the heat Q from C to A. Now since BC is an adiabatic process ስለሆነ QBC is 0 because it's adiabatic. This is 0. So this is QAB plus QCA. ስለዛ እነዚህን ሁለቱን ተርሞች ማግኘት አለብኝ። Now the process of QAB, which is simply an isochoric, is simply heating that takes place at constant volume. አይደለ? So the amount of heat that enters at constant volume is equal to QV. So QV is the amount of heat that enters the system during heating from A to B because of an isochoric process. Now, ስለዛ QAB is CV times N times change in T. Now, my change in T እዚህ ጋር ደግሞ so the change in T is TF minus TI. Now, በአይሶኮሪክ ፕሮሰሳችን ውስጥ our T final is TB አይደለ? ሲቀነስ initial is TA. But we know that TB is 3 times TA. መጀመሪያ ራሱ አይተናል። ሲቀነስ TA. So this is 2 TA ይመጣል። So this equals to CBN times 2 TA. Now CV for CV, which is simply and so CV for a diatomic gas is equal to 5/2 R ጋር እኩል ነው። So substituting this, I have QAB, which is 5/2 R times N times 2TA. Now in this value 2 but with afana, I have this equals to 5nRTA ይመጣል ማለት ነው። So this is my heat at QAB. So at QAB the value of heat is 5nR of TA. The next value is simply what is the Q at CA. Now Q at CA is a knife from C to A, it's an isobaric process. So that's that the amount of heat that it enters is going to enter at constant pressure ነው የሚገባው። So this equals to QP. So that's that QCA, which is equals to QP equals to CP times N change in T. አይደለ? So what is change in T? Now change in T is going to equal to the final, which is TA, ሲቀነስ the initial, which is TC, right? So that's that from this equation we don't have TC. So our next is going to be trying to find TC ነው ማለት ነው። So we have seen, and so ከዚህ ጋር እንዳየነው to find our value of TC we have to use ከእንደገና originally ያለው equation. So ከዚህ ተነስቶ ባለው equation, so ከዚህ equation ያለውን ስሰራው this is A, B and C ብለናል። So at this value we got at C we have to find originally ያሉንን values. So at here we have TC, we have PC, we also have some volume of VC. So I should find TC. TC ለማግኘት I can use the equation PCVC is nRTC ነው እንጠቀማለሁ። Now I know that at PCVC I know that PC is equals to PA አይደለ? So that's PA times VC. We have found VC እዚህ ጋር በዚህ equation ቀድመን በተሰጠን equation መሰረት we have found VC to be እዚህ ጋር. So V2 ማለት VC ነው። VC 2.19 VA መሆኑን አግኝተናል። ይሄን ያዙት። So we have our VC, which is 2.19 VA, which equals to nRTC ይመጣል። So this is 2.19 of PAVA, which is nRTC. Now we know that PAVA is nRTA መሆኑን አውቃለሁ። እዚህ በከተው I have 1/9 of nRTA equals to nRTC. So nR by nR, and I have my value of TC to be 2.19 TA. So TC is 2.19 TA ከሆነ my change in temperature, which is my final value, that's TA ሲቀነስ TC, is going to equal to TA minus of 2.19 TA, which is simply is going to equal to negative, going to equal to my values here, which is negative of 1.19 TA አግኝቻለሁ። So substituting እዚህ ያገኘሁትን my value of change in T into እዚህ ጋር ያመጣሁትን equation. So ወደ this equation ውስጥ ብከተው that is QP is equal to CP N times change in T ያልኩት equation ውስጥ እዚህ ጋር ያመጣሁት ማለት ነው። The one which I found here ብከተው my value of CP at this position is going to equal to NCP is going to be 7/2R times my change in temperature, that is እዚህ ጋር ያገኘሁት negative 1.19 TA ብሰራው this gives me negative 4.17 nRTA አግኝቻለሁ። This is what it gives me. So I have found my value of Q at constant pressure ማለት I have found QBA አለኝ። So substituting ያገኘኋቸውን values ሙሉ, that is substituting all the equations I have found so far, Q total, which equals to my value of QAB plus of QCA, because we have seen that QBA 0 መሆኑን አይተናል። And so when I substitute these equations into the given value, what I get is my value of QAB I have found to be 5nRTA, and I have found my value of QCA, that is when my value of QCA, sorry, QCA to be minus 4.17 nRTA, minus 4.17 nRTA. So if I take nRTA common, I have 5 minus 4.17, which is equal to 0.83. And so this becomes a 0.83 nRTA. So this is my Q total. Since this is my Q total, I know that my work is my negative of Q total. So the work is negative of 0.83 nRTA ይመጣል ማለት ነው ወይም or the same as to TI ወይም T1. So this is my work. So this is going to be the end of this video. That is question number 24. Question number 21 አይተናል።